Okay, so hi everyone. So let's see quickly the what is rotation. Another name given to this is the angular velocity. So in our fluid mechanics or in our aerodynamics, we have a important topic that is rotation or angular velocity, one in the same name. Okay, some book you will find in some book you will find this as a rotation, or in some book you will find this as angular velocity. So don't get confused. Both are one in the same thing. Okay, so understand the definition, then we'll understand the equation. Application point of view, what is rotation, what is angular velocity, we'll understand in the ideal potential flow chapter. Okay, and also then major application is involved in the our thin airfoil theory. Okay, so as of now we'll try to understand what is rotation, try to imagine what is rotation, then learn the formula, learn the equation. That is more than enough. Okay, from the application point of view, we'll when we start the ideal potential flow or thin airfoil theory, there we'll see in a detail. Okay, so in a simple word, also you can by intuition you can guess that rotation is the uh, also you consider the small fluid particle. Okay, we have a small infinitesimal fluid particle. So while flowing, while fluid is flowing, what happens, there is a motion associated, that is your translation and the rotation. Now what is the rotation? Rotation is that your fluid particle, let's say it is following some path. Okay, there can be rotation about a certain axis. Okay, now what do you mean by this, right? About the certain axis means when flow is flowing through some path or flow is flowing in some region, there will be rotation associated with its own axis. Okay, so now let's say you have this x, y, z. Also you can write this I cap, j cap, k cap. Okay, please understand this. So let's say you have a small fluid particle. Just to make you understand, I'm drawing it slightly bigger. Let's say you have some fluid particle, it is moving in some region. Try to get the explanation. So let's say you have a fluid particle and it is having this xyz axis, and now let's say your fluid particle is rotating about z axis, this about z axis. So how you will rotate, how it will rotate, it will rotate in y x plane, right? When you have a rotation about z axis, so it will rotate in, let's say, xy plane, isn't it? So if it is rotating about z axis, so it will have a rotation in this direction or in this direction. That we'll see, positive negative we'll see, don't worry about that. Similarly, try to understand in this way. Now let's say your fluid particle is rotating while flowing. Okay, it is not a stationary, while flowing I'm saying. Let's say this is the x-axis. Now it is rotating about the x-axis and it is rotating in the yz plane, this kind of rotation, or this kind of rotation is present. That means I hope you can imagine when you say about x-axis, so your fluid particle will be rotating in the yz plane. Okay, similarly now you can get it. Let's say if it is rotating about the y-axis, so it is rotating about the y-axis. Let's say y-axis is this one. Okay, it is rotating about the y-axis, so it will rotate in the yz plane. Okay, it will rotate in the yz plane, something like this, or in this direction, uh, something like this. I hope now you can understand this. So it will rotate in the, let's say, zx plane, or you say xz plane. Okay, so this is what your rotation is, and or in the or angular velocity. So if your fluid particle is moving and if it is rotating about the z axis, then it will rotate in the xy plane. Okay, similarly if it is rotating about the x axis, then your fluid particle will rotate in the yz plane. Similarly, about y axis, then zx plane rotation, in zx plane rotation. Okay, I hope this is clear. Now you can write, so rotation or angular velocity will be given as this omega. Okay, this omega, and this will also given by x I cap plus omega y j cap plus omega z k cap. So addition of the about the x-axis rotation, y-axis rotation or z-axis rotation will give you the total rotation or total angular velocity. That means while rotating the flow, if it is rotating, let's say this is more easy to explain you. Let's say if it is rotating about the z-axis, if it is rotating about the z-axis, so it will rotate in this way, right? Or it will rotate in this way. So it will have a some angular velocity. It will have a some velocity of rotation that is given by the angular velocity. Okay. Now, how you will capture mathematically? That is the question, right? So I'm not going into the derivation. Okay, derivation is not important for our understanding, for our solving numerical. Our equations and formulas are more than enough. Okay, so I'm not going to derivation. If you want, you can go through the FM White, Sengel and Simbala or John D. Anderson aerodynamics. Okay, but derivation is not required. So to write the omega x, that means about x-axis rotation. I'll come to the very important conclusion. Just have patience. Okay, about x-axis, when you write, you need to write in this way. Just see this. When you write for, when you have a rotation about y-axis, so you write in this way. I'll tell you what will be inside the bracket, what will come. When you have about rotation about z-axis, this is important. So when you write for x, let's say x, y, z. So when you have rotation about x-axis, here you need to write y and z derivatives. Okay, what is the meaning of the y and z derivatives? As I told you, this is how you need to write. When you write for x about x-axis rotation, derivative will be of y and z. This is how you need to remember. Okay, otherwise you will get confused. Similarly, when you write for y-axis rotation, about y-axis rotation, you need to write derivative of z and x, because sequence is important. Negative sign is present. That is the reason I'm telling you. That is the reason I'm emphasizing how to write this. Okay, so when you write for y-axis, then z minus x derivative will come. So dou z minus dou x. Okay, then when you're writing for about z-axis rotation, then x and y will come in a sequence. Okay, so you write x minus y, dou y. Okay, now the opposite velocity will come in the numerator. Okay, so what is the z? Okay, u v w. So what is the z velocity is w, so here w will come. Okay, similarly, what is the velocity for y? So you have a small v. So this is how you write for the derivatives. Okay, similarly, now you have for x, so write here u and here w will come. So this w and this w both are different. This is representing the your angular velocity. Okay, then you have the y. So for y you will write this as a small v, and for x you write this as a small u. Now this is how your angular velocities are written. Okay, that means if you want to capture the angular velocity or rotation of a fluid particle about x-axis, you need these two derivatives. Okay, so using these two, using these three, you will find the angular velocity for the for a fluid particle if it is moving. Okay, so okay, now please understand a very important condition. Now when you enter into the ideal potential flow theory or ideal potential flow chapter, okay, you need to have the your flow field will be the 2D. Your flow field becomes 2D. You will not consider the z axis or depth in that case. Okay, when you come to the ideal potential flow, your depth is not considered. Depth is considered as a unity. Okay, so your angular velocity. Okay, pardon me for this. So your angular velocity about z axis, because you don't have a 3D, right? So z axis will become angular velocity. Z axis will become 0. This will become 0. Okay, once this becomes 0, once this becomes 0, you'll end up getting this as a dou v by dou x minus of dou u by dou y equals to 0. Now this is very important conclusion we have arrived at. So now please take this as a very important. So when you have this condition to be 0, that means when you have a 2D flow, or when you have the angular velocity on z-axis, about z-axis 0, in that case you will have this condition, and once you take this negative term into the right hand side, you will end up getting this as a this condition. From now on, please make this as very important. By heart this equation. This is the very important conclusion we have arrived. That condition is the condition of irrotationality. Okay, so let me write this. Condition of irrotationality. Okay, for 2D flow, for two-dimensional flows. Okay, mark this as a very important conclusion or condition for irrotationality for 2D flows. Okay, so if someone asks, or if someone have given you the velocity field or velocity vector, just check for this condition for 2D case. So when this condition satisfies, okay, for a particular velocity vector, if this condition satisfies, that means your flow is irrotational. Flow is not rotating in the fluid flow condition. But if this condition does not satisfy, then you will directly say confidently that my flow is rotational. That means flow is rotating in the xy plane, okay, about z axis. Okay, I hope this is clear. Now what I will say, please block this equation. These three equations are very important for our exam point of view for solving numericals. So please block this one and this one as well. And you should know that what is this condition, and this is for 2D. Okay, this is important. Don't worry, you will come to know once we start study about the potential flow theory and the thin air foil theory. We have a major application in the thin air foil theory about for a rotational angular velocity or vorticity, then the circulations. These are all important things we need to understand to develop the thin airfoil theory equations. Okay. Now one more thing that we need to understand. Now, what is vorticity? Now what is vorticity? Vorticity is denoted by this symbol. Okay. Now I'm not good into the derivation or definition as of now. Again, I'll tell you the same thing. Once we start discussing the thin airfoil theory, this will start making more sense. Okay, that is the reason I'm not giving you the explanation, but as of now, understand the equation. Okay, equation is important to develop the thin airfoil theory equations. Okay, so vorticity is given by this zeta, or you say xi, whatever. It is a curl of velocity vector. Okay, curl of velocity vector. So this is very important thing. Please mark this. Please block this. It's a curl of velocity vector, or you say curl of velocity vector v. Okay, now I'm coming to the very important conclusion about the vorticity. Now when you write this into the mathematical form, this can be written as dou of dou x. I hope you are aware of how to open the curl of any velocity or curl of any vector. And let's say you have u, v, then w. Okay, now when you open this, you will come to know. So when you open this, for let's say we are writing for I, so this will be gone and these two will be left out, right? So don't worry, I'll tell you which equation to learn, what to skip. Okay, then you have a, okay, then when you write for j, you need to neglect this minus of, you have a j cap here, then you have a positive sign with. When you write for k, you need to neglect this one, and the derivatives are this. I hope I have written it correctly. Okay, so when you open this determinant, you'll end up getting this equation. Now please see this carefully. Now when you see this, okay, now understand these terms. Okay, these terms are, so now see this. Now if you see this carefully, this is reverse of that means negative of angular velocity of y. about y-axis. And if you see this one, it is omega z, isn't it? This component is omega z. So now we can write what we can do. I'll reverse the position. Okay, so this will become z, this will become x, and this will become u, this will become w. I'll make a positive sign. I can do this, right? I hope you understand. So now if you see, these are twice of omega x, this is twice of omega y, this is twice of omega z, right? So I can write 2 omega x I plus 2 omega y j plus 2 omega z k, right? Now what I'll do, I'll take common 2. Now I'm coming to the very important conclusion. Please focus on this. I hope I've written correctly. Yeah. Okay. So now if you see this carefully, what this is telling us. Now I know my omega vector is this one, right? Right. It is addition of all the axes. So now my vorticity is nothing but twice of angular velocity or twice of rotation. I hope now you understood. So from now on, you should remember that vorticity is the twice of the angular velocity. So vorticity is also a vector quantity. Okay, please remember this. Then your rotation or angular velocity is also the vector quantity. Okay, acceleration was the, we know that acceleration was a vector quantity. Okay, so I hope now it is very much clear. So please by heart this one and this one. Okay, one more important conclusion from here. Now if your velocity field at any point in a flow, let's say vorticity, which is our curl of v, or it is can be written as in this way. Okay, so if we get this condition, okay, of velocity, what you do, you take this you try to solve for this velocity vector of a cross product using this, as we have written here. And if it is going to non-zero, okay, first thing, if it is going to, let's say it is not equals to the 0, so what we say, at every point in the flow, okay, please write this, at every point in the flow, if this condition is satisfying, or if your velocity vector, if you are taking this component, if it is not 0, then we say our flow is rotational. Okay, so let me write flow, we call it as a rotational flow. Okay, very important deduction. Please write this has been already asked for your GATE exam, in your GATE exam. Okay, it is when, if this condition is satisfied, then we'll call it as a rotational flow. That means it implies that the fluid elements have a finite angular velocity. That means, let me write this, fluid element is having finite amount of angular velocity. Please write this small thing. They can anytime they can introduce or they can ask in your GATE exam. Okay, so for 1 mark. Now second condition, if this condition is satisfied and becomes 0, this condition satisfied and becomes 0, then we'll say at every point in a flow, okay, at every point in a flow, my flow will be irrotational. Okay, in that case, let me write flow is irrotational. Please write this. You must keep this in a formula sheet, okay, or your notes. Okay, flow will be called irrotational flows. And in that case, I'll say if this condition is satisfied, it implies that fluid element has no angular velocity, rather their motion through space is pure translation. Okay, it implies, let me write this as well, you should write this, guys, in your notes. no angular velocity, no angular velocity, rather it is having their motion is pure translation in a space. Space. Okay, just I hope now you can understand. Okay, no angular velocity, having finite angular velocity in these cases. I hope now this is making more sense. Now please understand why it is important to study the irrotational flow and rotational flow. What is important? Why it is important to have the study and to have the equations for rotational and irrotational flows. Now please understand this. Now study of irrotational and rotational becomes important in our aerodynamics or in our theoretical theoretical aerodynamics. When we go for theoretical aerodynamics, this irrotational, rotational, and your angular velocity, vorticities, these characteristics of fluids becomes very important when we go for classical aerodynamics. Okay, but for our GATE exam, we need to understand the equations and formulas are more than enough than these theory points which we have discussed. Okay, so now why rotational and irrotational flows? So analyzing the analyzing your irrotational flow is more easy compared to the rotational flows. Now please understand this. Analyzing the irrotational flows are more easy to analyze the rotational flows. Now from the application point of view, when let's say your let's say you have a flow over an airfoil or over a wing, subsonic flow throughout, subsonic flow. Okay, subsonic flow you have. So when you have a subsonic flow through the airfoil, what happens that near this surface, let me take near this surface, your flow will be rotational due to the viscous layer or due to the boundary layer formation. Your flow will be highly rotational, but except these surfaces, your flow field will be completely irrotational. Okay, that is the reason to understand to understand this flow field, okay, over the airfoil in subsonic condition, we need to develop the equation, or we need to have understanding of a irrotational flows. Okay, to analyze the this region, except this region, except this region, or to the surface area, we need to analyze this area, this region. To analyze that, we need the equation of irrotational flows or understanding of irrotational flows. Okay, one more example I'll give you. uh, Subsonic and supersonic flow through the city nozzle. Subsonic flow and supersonic flow through city nozzle. So again, near the surface area, again near the surface area, you have a boundary layer formation. Inside the boundary, let's say, let me make it bigger slightly so that you can understand, but it is not so thick, okay, in reality. So inside the boundary layer, your flow is rotational. So you need to, and that layer will be very thin, very small region will be the rotational region. Okay, due to the viscous effect or due to the boundary layer formation. Boundary layer formation is ultimately caused by the viscosity, right? Viscous effect. So most of the area will be the irrotational, and small area will be rotational flow. So to analyze this city nozzle, our most of the region and the important dominant region will be of a rotational flow, and rotational flow equations will be applied in that case. Okay, if I'll give you one more example. So I hope you understood why rotational irrotational flows are important, where it is formed. Okay, I hope this is clear. I hope you understand. If you're having any doubt, you can go through once this lecture. If it is not clear, then you can message me or you can ask your doubts. Okay, so I'm assuming that you are understanding, and please block this important equation which I told you. Let me, so this equation, very important. Okay, then this condition for 2D flows, then this condition, then this important deduction, then these two important rotational irrotational flows, very important. And if from the interview perspective, if you are appearing, then this kind of explanation they will be expecting you to know. Okay, so if you are very curious to understand the rotational flows, aerodynamics, then you should have this kind of understanding. Okay, so let's meet in the next video, guys, with the probably we'll start the circulation. Okay, let's meet in the next video. Bye bye.